Hello there, I'm Conrad and welcome to this video series. Today we're going to look at making a fin assembly for a minimum diameter high power rocket using forged carbon fiber components. This is the first part in this series and we'll kind of touch on the design, but before we do, we'll review some of the traditional construction methods for making such a fin assembly. There's actually these traditional construction methods that inspired me to think outside of the box on how to do this differently. Once we've done that, we'll review the actual design, and then that'll allow us to look at some of the tools and consumables we'll need for this project. And then we'll dive in and we'll actually make our first part. So welcome, and let's get started. Okay, so let's dive in. As mentioned, the concept of this project is to make a fin assembly for a minimum diameter high power rocket. And more specifically, a modular fin assembly made from forged carbon components. A fin assembly is also known as a fin can, since it can technically be slipped onto an airframe or even directly onto the rocket motor. The rotating design above is what I'm trying to make, but let's take a step back and talk about how I got here. Here you can see an example of a 3-inch minimum diameter rocket that I built using traditional methods. It really is a pretty rocket. It is strong, stiff and light. It'll fly on a 75mm Aerotech L2200 motor, which has a total impulse of around 5,000 Newton seconds. And will launch this rocket to about 16,000 feet with a max velocity of Mach 1.9. So let's talk about the traditional construction methods. Here you can see the fin is epoxy directly onto the airframe using a alignment jig to make sure that the fins are properly aligned. Once the fins are all epoxied on, we create fillets with basically epoxy that's filled with a filler, which is then once set, it's sanded down and shaped to create like an airfoil shape. Next up is preparing the tip-to-tip carbon fiber twill layers, which will be epoxied onto the airframe we saw in the previous clip. Everything is wetted out and we add a layer of peel ply, which will help separate all the layers at the end. Then we also add a layer of breather fabric, which will help draw out excess epoxy during the vacuum bagging process. Everything is then placed into a vacuum bag and a full vacuum is drawn for the duration of the cure, and will create an extremely strong bond between all the layers. This is the part out of the vacuum bag, and you can see the initial surface finish is pretty rough. We'll go into various cycles of adding a thin layer of epoxy and then sanding it down and keep repeating that until you get this final high gloss look. This is a 10,000 foot view on this traditional method. I'm not going into all the details here, but it can definitely be seen as a complex and very labor intensive process, and definitely a bit of an art form, especially for first time implementers. And then there's the cost involved for the required consumables and equipment. So that got me thinking, how to make this easier. My critical engineering mind asked, is there an easier way to build a minimum diameter rocket? The dream or vision I have is to create a fin assembly that is easier to make than using these traditional methods. Something that can be bolted on, so to speak, but that still meets the core requirements of being made from carbon fiber, that has the ability to have complex airfoil profiles, and that can withstand Mach flights. I started by designing a full fin assembly in Fusion 360 and realized that producing this in sizes larger than a 38mm rocket will be practically impossible. 3D printing it does not provide the strength, and milling it out of a single block of aluminum is impossible for an amateur shop. Here's an example of an SLS 3D printed fin can. It is a great prototype. However, There's a lot of flex in these fins, so definitely not something that can withstand high mark flights. I mean, the alternative is to actually just do a tip-to-tip carbon on this, but then that kind of defeats the purpose of a slip-on fin can. So the answer is to deconstruct. Take the design and break it into smaller pieces. I took the 3D model and deconstructed it into the fins and the bits that go between the fins. These I will call the brackets. In a 4-fin rocket, you'll have 4 fins and 4 interconnecting brackets that hold it all together and effectively creates a can or assembly that slips over the airframe. Everything is then bolted together, as you can see. Technically, these components are now small enough to be 3D printed, but any type of 3D printing, FDM, SLA, SLS, that is not, when you're not printing in any type of metal, will not really provide the strength needed for mark flights or flights that will result in high dynamic pressure on the airframe and specifically the fins. I mean, yes, it could work for rockets that are designed to go slower, but people that fly minimum diameter rockets usually want to go really fast, and flutter is not your friend with these type of flights. I evaluated various construction techniques and settled on a method known as forged carbon construction. This method allows for creating incredibly strong parts, and it also allows you to create complex shapes that would be hard to make in any other way. Yes, these parts could be made using the CNC mill, and I'm still going to explore this as an option, and I'll create a future video on this process. So technically nothing is forged. There's no heat or furnace, and this is really a compression molding technique. A 2-part mold is created from the part. Carbon and epoxy is added to the mold and compressed to create a really strong bond between the fiber and the binding matrix, or the resin. Then a combination of chopped carbon fiber, also known as chopped tow, and carbon fiber twill weave is used where 80% of the fiber content is chopped tow, and I'll be using 2x2 4K twill carbon fiber. Making these molds using 3D printing technology sounds simple, but this has certainly been a challenging journey. Starting with making the 3D printed molds using my Bamboo Labs FDM printer, printing in PETG, and then later moving on to making the molds in resin using my Form Labs Form 4 printer. Purely because printing in resin is 10 times faster, and if done correctly, the dimensional accuracy on a resin print far exceeds printing in PETG, and that's a lot stronger. Honestly, the strength of a resin print is a key factor in driving the final dimensional accuracy of the part you're making. Like under pressure, there is no warping of the mold compared to a PETG print. And I'll make a separate video on this whole mold making process, since I can spend a lot of time explaining this journey of discovery. Needless to say, there are lots of failures and learnings. Okay, so let's dive right in and make one of these brackets. I'll run through the end-to-end process here, calling out tips and tricks as we go, and starting off this process looking at the consumables and tools needed for this process. So first of all is our 2-part mold, and it really is the star of the show. This is a 3D printed resin mold, as mentioned. Next critical component is our carbon fiber. This is the long fiber chopped carbon tow from Easy Composites in the UK. The fiber length here is about 1/2 inch compared to the more traditional chopped tow, which has a fiber length of about 1/8 inch. If this stuff is mixed with epoxy, it really creates a paste, and it can really be seen as a high strength filler, and you don't really get the strength that kind of the longer fiber tow provides. And then we also have the 4K 2x2 twill weave that was supplied by Fiberglass here in the US. So let's talk about epoxy. I'm using a low viscosity infusion epoxy, specifically the System 4500 from Fiberglass. and I'm using the infusion epoxy since it flows really well, and I found it easy to draw out trapped air, which is a critical part of this process. Also using a 70-minute pot life hardener allows me to take my time making these molds. There's no rush. And this entire process I'll show in the next part of this video. Next up is the release agent. This is a critical part of the process, since the release agent will allow you to separate the final product from the mold, and the mold to release any excess epoxy. Without this release agent, you can dead in the water. I'm using the RW4 spray release wax from Easy Composites in the UK, and honestly this stuff is like magic. I've had great success working with this. I've also had good success with Man Release Technologies Ease Release 200, as well as the Smooth On Universal Mold Release. Yeah, just take your time in making sure you've got full coverage. I spray this on and then let it dry for probably half an hour, and then just follow it up with one more coat. And every time before the next round of molding, I will give it one extra coat. Next critical component we'll need is a vacuum chamber, as well as a vacuum pump. The chamber is used to extract air from the epoxy, as well as the air that's trapped between the carbon fibers. The final critical tool we'll need is some form of press. You could use a vise or some clamps, but I found that using a press like this gives you great control over the pressure applied. It also allows you to release the pressure and kind of keep cycling that pressure. So definitely a critical tool. So let's talk about the ratios. How much carbon and how much epoxy? This is a simple formula, starting with the volume of the part we're making, and we can find that by looking in Fusion 360, find the properties, and you can see here the volume of this part is 1.738 cubic inches. And then we take this and we do some conversions. We convert that to cubic centimeters, gives us 28, and then the overall weight of this part will be the cubic centimeters times 1.4, and of this 39.8 grams, 60% of that will be carbon, and 40% of that will be the epoxy. Then also I mentioned earlier that 80% of the carbon load will be chopped tow, and the rest will be twill. But this is a bit of a moving target based on the shape of the two layers of twill and the resultant weight of these layers. You can see that it's closer to 75% chopped to 25% twill. So we start off by mixing the epoxy and the hardener, and we'll do this by weight. And the secret here is that you really want to double up on the total epoxy, or even 70% more than the calculated value. If you were just to use the calculated value, you'll end up with lots of dry spots and voids in the final part. The reality is there will be waste. In the end, you'll still end up with the calculated value of epoxy in the final part. Since under pressure, the carbon stays constant, since it has nowhere to go, but the epoxy is pressed out. So the calculated value of epoxy is around 16 grams for this example, but I'm adding around 70% extra, and that's just based on experience. And the reality is that it's about 70% waste, and the objective is to try and reduce this over time. Okay, starting off, we're going to wet out the bottom of the mold, kind of working it in there, getting it in all the little areas. Just helps to ensure that we don't have any dry spots in our bottom layer. And the next part is to add our first layer of twill carbon fiber. Again, this is different from the way I've done it in the past, where I started with the chopped toe in the bottom. Kind of had mixed results. So just changing it up, adding the one layer of twill in the bottom. Yeah, just taking my time to work it in there, just getting it all laid up, just making sure that, you know, the fiber orientation is kind of 90 degrees to kind of front and back, side to side. Just kind of working it in there. And then once that's done, we're going to move on to the chopped carbon fiber, also known as tow. And honestly, this process is a little bit of an art. Working with this stuff is really tricky. It first of all wants to stick to everything. It gets airborne, so one of the big things is to wear full respirator. I have air filters running on the side, kind of just cleaning up the air. But yeah, the art here is just to kind of work it in and get a feel for it, because the stuff loves to clump together, and you don't want clumps. So just kind of spreading it out evenly, kind of get a feel for where the clumps are, and then just kind of working it into all the areas. And then the next part would be to do the wetting out, adding the epoxy. Kind of just finishing this up here. All right, here we go. Kind of wetting out the chopped carbon fiber, and honestly, the best way I've found to do this is just to kind of drench the stuff. Start dry and then drench it. Just get it in there. I've tried to do this, you know, to try and wet it out completely beforehand. And honestly, this stuff, especially the long fiber tow, just creates a matted mess. You end up losing a lot of epoxy. And here you can see I'm going to really regret life choices here. Kind of touching the stuff. Once you touch the stuff and it's already wetted out, it literally wants to just stick to everything. So again, this is why I've found is just to put it in dry, drench it, and then make it settle. So the one way I've found is just to add heat. This helps with the viscosity of the resin, kind of helps it flow. Yep. So just adding the heat, just making sure that, you know, we don't blow the fibers everywhere. Next up is into the vacuum chamber. Running full vacuum, many cycles, probably 2 or 3 cycles. Just trying to suck out all the air, because the thing is, the nature of the tow is that it's aerated. It's like aerated. There's a lot of air trapped between kind of all the fibers. So now it's the kind of the race between getting all the air out and having all the epoxy kind of flow into, you know, into all the areas. Once that's out, we go into the next part of kind of adding the final layer of the top layer of carbon fiber twill. In the past, I would have done 2 layers on top, and this round of experimentation, 1 layer on the bottom, 1 layer on top. Again, I'm putting the twill in dry. I might experiment with, you know, wetting out the twill before. I'll see. But here I'm just going to add just one final bit of epoxy just at the top. This will help kind of just with that kind of wetting out of the kind of the top layer. And again, kind of just getting in there. Then using a brush, kind of really gently just kind of spreading out the epoxy Really be careful here to kind of not disturb your fibers, because if you kind of mess up your the fiber orientation here, kind of pull at it, kind of lose that classic carbon fiber look. Okay, once that's done, again back into the vacuum chamber here, adding heat, again just helping the epoxy flow, and it also really I don't know if it kind of annoys the epoxy, but you know, once it's heated up, you pull a vacuum, which will happen right now. You can see the epoxy gassing out. This stuff is nasty. My vacuum pump and system, I've got a pipe that runs outside just to get rid of those toxic gases. But yeah, leave it in here 5 minutes or so, various cycles, full vacuum, 27 to nearly 29 inches of mercury, and you can see kind of the bubbles forming, you know, just as the air is pulled out of the carbon, between, you know, obviously still trapped in the toe, in the twill, and yeah, you want to get rid of the air as much as possible, because if you've got trapped air bubbles, and this is kind of my first experimentations, I pulled it out and I had air bubbles, you know, that got trapped, and it kind of ruins the surface finish. You can see here nearly, it's about 28 inches of mercury. All right, next part is kind of finishing the mold. We're adding a homemade clamp, kind of just pulling the kind of two bottom halves together, and going to add the piston, kind of the first part, the front one, and you can see here, once I switch to that view, you can see the kind of the tolerances here between the kind of what I call the piston and kind of the mold body. I literally have 1,000 of an inch, you know, between these parts, and that's kind of the magic of creating these molds from 3D printed resin. You know, once you figure that part out of how, you know, you can actually get incredibly high tolerances out of these molds. But it's a bit of a curse as well. Like those tolerances also prevents you from, you know, pushing out excess epoxy as well as the trapped air. So, you know, with my experimentation here, I think future versions of this, I think I might go to like a tolerance of like 4,000ths of an inch. Just give it a little bit more clearance for epoxy to escape as well as air. All right, so here just adding a little bit of clamping force, not a lot, just kind of keeping these two halves together. And then this is the part where it's kind of slowly adding pressure, just by hand, just kind of pushing on it. And this is another thing I found is in the past I would kind of just add pressure, keep adding pressure, and just keep adding pressure. But like with this round, actually, I think this is kind of maybe part of the magic here is to keep cycling the pressure. And I've seen, especially once it goes into the pressure, if you cycle the pressure, you know, apply pressure, release pressure, apply pressure. I'll cut to a shot here where you can see the bubbles forming. You can see the air escaping. This is after a number of rounds of applying and releasing the pressure. Because you want to get rid of that trapped air. Like if an air bubble is trapped, you know, it sits in your final part and it kind of ruins everything. All right, we're on to the next order of operations to basically pull the part out of the mold, kind of get rid of this custom bracket or clamp, and then just have a look at the mold, which looks really good. You can see at the bottom here the excess epoxy that was pressed out. In the future, definitely want to reduce this waste. And yeah, then just kind of working my way around this edge where the epoxy was basically pressed out. Kind of need to get rid of this so I can get a plastic tool in that edge, so I can start removing the top part of the piston. Again, patience is needed here. This resin mold is really strong from a compression perspective, but a sharp blow will definitely crack it, and I've done that. So yeah, definitely a process of just going around patiently. Final bits removed, and gonna just transition here to start removing some of this excess epoxy that's caught on the bottom. Just start cleaning up the mold. Again, in the future, big priority is to reduce this waste. Kind of finding that right balance of, you know, wetting it out versus kind of the waste. And then we're on to kind of separating the piston from the mold using these plastic trim removal tools used in cars, basically, to remove trim. Works really well. Kind of this big one specifically is a kind of using it as a lever. Really satisfying to see this thing come apart, and then once that pops out, we get our first look at what the part looks like. And this one came out really beautifully. Probably one of the best surface finishes I've had so far. Kind of all the changes I've made leading up to this point has kind of paid off. There's definitely, you know, obviously some surface imperfections still, but that'll be sanded out, and then, you know, a couple of layers of clear coat, kind of just make it, kind of finish it off, and then finally kind of breaking the mold part in two. Again, this is where the trim removal tool really comes in handy. Giving a couple of light taps, and then finally, you know, there's this kind of satisfying crack as the two parts separate right there. Yep, and then just again slowly just moving the two parts, and then yeah, there it is. First look at the kind of the bottom. Very happy with, you know, the twill on the bottom. Surface finish looks and feels great. Yeah, extremely happy with the way this one came out. And then just final effort here to release it from the mold. And the mold itself looks great, ready to be reused. A little bit of a cleanup, but the part looks great. You can see the you know, kind of the flash, the excess epoxy, and some of the fibers that were trapped, you know, between the piston and the mold. Not a lot of waste there. Happy with that. And next thing is to start. I'm going to take like heavy duty scissors, just kind of work my way around the edge, cutting away this excess. And then once I've done that, I will probably just use a little hand file, kind of finish the edges off, and then you know, then it's on to, you know, sanding it down and finishing the part off. So join me in part 2 of this video series, where I'll make a forged carbon fin. I'll also go on to show some of the finishing techniques that gets us to this high gloss carbon fiber look. And then finally, we'll make the mounting holes. This turned out to be the most complex part of this project. So thanks for watching, and I'll see you next time. Oh, and before I forget, it would be great if you can like this video and subscribe to my channel and follow along on this crazy journey of mine. Cheers.